the microphones. Dr. Tara Shears is a Royal Society Research Fellow at the University of Liverpool. She gained her PhD at the University of Cambridge in 1995. Since then, she's played a key role in large experiments, OPAL at CERN, and also at CDF at the Tevatron Collider at Fermilab near Chicago, and she's still working on that experiment, which is the biggest accelerator at present working. In 2005, Dr. Tara Shears received the Cavendish Medal for the Outstanding Young Research Fellow, and since then, she has been working at the LHC. This is a very exciting time for particle physics because the LHC, this huge collider, is about to be commissioned at CERN after many years of preparation, at least 20 years. So it's, without further ado, it's a pleasure to introduce Dr. Tara Shears, who will talk on the LHC.
Thank you. So hi, everybody. This talk is about the building blocks of the universe. It's about the fundamental particles that we think are matter's smallest constituents. Because in particle physics, we try and understand the universe from the microscopic level. We think in particle physics that everything in the universe, everything, all matter, is made of the same fundamental constituents. And it's our aim to identify what these are and how they behave. Now, we already know quite a lot about matter and the universe, but we also know that there's much more to understand. And it's for that reason that this talk is also about the LHC. So as Alan has just told you, the LHC is our new particle accelerator. It's the most powerful particle accelerator we've ever built. And the LHC is the facility we're going to use to strengthen and deepen our understanding of matter and the universe. So in other words, this talk is going to be as much about what we don't know as what we do know, and how the LHC is going to help us find out more about everything. So I'll start off this talk by talking about the particle physics, because that underlies everything. I'll tell you what we understand about the universe so far, and then perhaps more importantly, I'll tell you what we don't understand. And I'll tell you about 3 of the most pressing questions that face us in particle physics nowadays. And then, having told you about all our problems, I'll then show you experimentally how we try to address them, how we try and find answers and solutions to them. And that will bring us on neatly to the LHC itself. So I'll describe what the LHC is. I'll tell you about the particle accelerator and how we use it to generate the fundamental particles that we want to study and understand. I'll tell you about the experiments that we build there to detect these particles. And then I'll finish my talk by telling you how we make sense of the data that we collect in our experiments, what we might see in our data, and how we might go about making the sorts of discoveries that will allow us to learn more about matter and the universe. So let me start off with the particle physics. And before I tell you what we understand about the universe at the moment, first of all, I want to set the scale of the smallness of the fundamental objects that we're talking about. And I find it most helpful to do this by means of a sort of reference scale. So this is my reference scale. It's a person, and it's a sort of physicist person. They're only about 1 meter tall. This is my scale of reference. So if we were to look at this person, the smallest thing that we could see with our naked eye would be the size, the thickness of the hairs on their head. A human hair is about 100,000 times smaller than a person. And if we could get powerful microscopes so that we could zoom into a hair by the same amount again, look 100,000 times into a hair, we would see that a hair consists of atoms. You could fit about 100,000 atoms across a human hair. And if we could get an even more powerful microscope, we would see that an atom isn't fundamental. It's not a fundamental particle. And by that, I mean it has structure. It consists of other things. If we could look deeply into an atom, we would see at its core it has a nucleus, which consists of particles we call protons and neutrons, and these are orbited by electrons. So picking a more powerful microscope and zooming into here, we'd see a proton, for example. A proton, a constituent of an atom, is about 100,000 times smaller again than an atom. And if we could pick an even more powerful microscope, and this is where particle accelerators come in handy for reasons I'll tell you later, then we would see that a proton's not fundamental either, because that's got things in it. It consists actually of 3 fundamental particles that we call quarks, and quarks are at least 10,000 times smaller than a proton. Now, quarks are an example of something we believe to be fundamental in particle physics, and that's because we've never been able to look inside them and find something else. They're point-like to us. And when I say they're at least 10,000 times smaller than a proton, we haven't actually been able to measure them. They're so small that the 10,000 times just comes from the limit of our experimental resolution. So to set the scale of these fundamental particles, to fix it in your mind, a fundamental particle like a quark is almost as small compared to an atom as an atom is compared to you. That's the size of particle that we're dealing with, that we're trying to understand in particle physics. And that's the sort of thing whose behavior we're trying to understand. So that's set the scale for you. Now I'd like to tell you about what we know already about matter and the universe. And in particle physics terms, you can express the universe very, very neatly. So we think that all matter in the universe is formed out of 12 fundamental types of building blocks, 12 different types of fundamental particle. Now, this might not look like much to show for 40-odd years of research, but then we're great reductionists in particle physics. We really can get down to this level. So of these 12 fundamental particles, 6 are of a type that we call quarks, and 6 are of a type we call leptons. And the sorts of fundamental particles that are most common around us here on Earth are up and down type quarks, because combinations of these form protons and neutrons that we find in atomic nuclei, which are then orbited by electrons to make atoms. And we know that everything we see around us on Earth is made of atoms of one sort or another. And these other fundamental particles are more common in higher energy environments than we typically have around us here on Earth. So this is what particle physics says about the universe, but it's no good just unraveling matter to its constituents. In particle physics, we also want to know how to put these things back together again to make the universe look the way it does. And we think that there are 4 fundamental forces that do this job. And let me tell you about those. So the first force is the weak force. The weak force is responsible for radioactive decay. And the weak force affects every single one of our matter particles. And we even have a picture in particle physics for how this force works. We think a force is exerted between matter particles by means of the exchange of a new type of particle, a force-carrying particle, which we call a boson, that's exchanged between the matter particles. And so for the weak force, we have 2 force-carrying particles to do the job, which we call the W and the Z boson. Now, any of these fundamental particles that have an electric charge also feel the electromagnetic force in addition. The electromagnetic force is conveyed by particles called photons. And fundamental particles called quarks also experience the strong force. And it's a strong force that's responsible for keeping positively charged protons from breaking apart atomic nuclei, because it's stronger than the electrostatic repulsion that those particles feel. And this force is conveyed by particles called gluons. So that really is more or less the universe according to particle physics. That's what we've deduced about matter at its deepest level. At least this is what we consider in particle physics. Now, I did say that there are 4 fundamental forces, and I've only told you about 3, and that's because I haven't mentioned gravity yet. And we know that gravity exists because gravity is responsible for the large-scale structure of the universe. It's what keeps us stuck to the surface of the Earth. But in particle physics, the distances that we deal with and the masses of our particles are so small that gravity is so much weaker than the other forces that we just tend to ignore it. So in the particle physics universe, we don't tend to consider gravity. So the universe, according to particle physicists, looks something like this. This is our recipe for creating anything in it. So if you take anything you can find in the universe, disentangle it to its constituents, you would expect it to consist of these particles. And if you were to go back right to the beginning of the universe, just after the Big Bang, you would find that, in fact, the universe is populated by these fundamental particles, because conditions then were so energetic that these particles it wasn't energetically viable for them to lock into other forms of matter, like atoms and stars, like they have done in the universe today. So we've not only identified these fundamental constituents of nature, but we also have a theory that describes how they interact with each other, how a force and a matter particle interact together. And we can use this theory to predict what we see in our experiments. So we can use our theory to predict how often we might expect a force and a matter particle to interact and how strongly it might do so. And this theory is really, really, really good. It's so good that we've never yet made an experimental measurement that disagrees with any of its predictions. This theory is so good that, somewhat hubristically, we called it the standard model of particle physics. Now, with a name like that, you know we're heading for a fall. And this is all very nice, but we also know it's not the whole story. We know, for example, that this theory is not complete. I've already shown you that we don't include gravity in it, so it can't possibly hope to explain the whole universe. And not only that, but good as this theory is at predicting what we might see in our experiments, it doesn't actually explain very much about the universe. And for that reason, it's not a very complete theory at all. So we know there must be something more to our understanding of matter. There's much more to find out. And that really brings me to the end, more or less, of what we understand and know in particle physics. And now I want to tell you about the problems that we have. And I'm going to tell you about 3 pressing problems to give you an idea of what it is that worries us, what keeps us awake at nights, that we try and solve in our sleep. So the first problem I want to tell you about concerns a very, very fundamental quantity, and that's mass. Mass is a fundamental quantity. We all have it. It's what gravity acts on. And our fundamental particles have mass as well, and we know this because we can measure it experimentally. But what we don't know is what causes our fundamental particles to have mass, what process gives them mass, and what causes them to have the value of mass that they do. And I've tried to allude to the different masses of these particles by the different sized blobs I've put down on this page. Now, we don't know why our particles have those particular values of mass, and in particular, we don't know why the mass of one of them, the top quark, is so much bigger than the others. A top quark has the same mass as an atom of gold, and yet it's 1,000 million times smaller, at least. And we don't know why this is. So problem number 1 is this question: what is mass? What causes our particles to have mass? How can we understand it? And in fact, we do have a theory that attempts to explain this, and it's not a new theory. It was first put forward in the 1960s by many people, amongst whom was a man called Peter Higgs. And this theory tries to explain mass as a property that one of our fundamental particles gets by means of its interaction with a new type of particle. And this new type of particle is called, somewhat unimaginatively, a Higgs particle. So our fundamental particles obtain their mass through interacting with this new type of particle, which is present throughout the universe. And the amount of mass that they get, which was something else we want to understand, just depends on how strongly they interact with this Higgs particle. That's what the theory tells us. Now, I'd like to try and give you a picture for this, for how we think in particle physics this process happens, and I'll try and do this by means of an analogy. Now, you shouldn't take this analogy too literally, because it's not exact. It's only intended to give you a picture. And the way the analogy works is as follows. I'm going to compare 2 things. I'm going to compare the movement of a body, a person, through different sorts of media, and the movement of a particle through the universe that's populated by Higgs particles. I'll give you a couple of examples, and you'll see what I mean. So this is example number 1. This is a picture of a skydiver. She's moving really, really fast, and she's moving through the air. And the air's not stopping her. She's not interacting much with it to slow her down. In terms of our analogy, She would be a particle zipping through the universe at huge speed. She wouldn't be interacting much with the Higgs particles around her, so she would behave as if she had a very light mass. She would be a very light particle. Let me give you another example, and I'll take a person and put them in something that they will interact with more. Let's take our person and put them in water and make them swim. Now, of course, they move more slowly, but they also experience more interaction with the water around them than the skydiver did when they were falling through air. In terms of our analogy, this person swimming is equivalent to a particle moving through the universe, but interacting more strongly with the Higgs particles around them. They feel more interaction, they move more slowly, and in terms of momentum, it means they're behaving as if they have more mass. So because there's a stronger interaction, they're a more massive particle. And that's the sort of picture we have in our heads for how our fundamental particles get mass. So the more massive a particle is, the more strongly it's interacting with the Higgs. And so that for a particle like a top quark, which is very massive indeed, that's equivalent in our analogy to taking our test person and putting them in something very sticky indeed, where there's going to be lots and lots of interaction to stop them. So this theory tells us that mass is a property mediated by this particle, the Higgs particle. And in fact, we've included this theory in our standard model of particle physics. So to some extent, it plays its part in every successful prediction that's been verified by experiment. However, it's only a theory. And it's only a theory because it's one experimental observable has never been seen. We've never seen a Higgs particle in our experiments, despite man years of searching for it. It's very important to us. And this is really worrying and concerns us because if we don't see a Higgs particle, of course, we can't be sure that it exists. And if the Higgs particle doesn't exist, then the theory is wrong. And if the theory is wrong, not only do we not understand mass, but more worryingly, the theoretical framework by which we understand all of particle physics is incorrect. So that's why it's such a big problem for us. And that's why particle physicists have almost as their first priority this search to try and find the Higgs, because that will tell us if our understanding is correct or not. So that's just the first problem. The second problem I want to tell you about is slightly different. It concerns antimatter and why there's so little of it in the universe today. And the problem is as follows. At the beginning of the universe, we think that equal amounts of matter and antimatter were created in the Big Bang. And yet, if you look at the universe around you now, it only consists of one type, which we call matter. And we know this because if matter and antimatter come into contact, they annihilate, and they release tremendous amounts of energy. So, for example, if you had 1/4 gram of antimatter meeting 1/4 gram of matter, and these were to annihilate, the energy of this annihilation would be equivalent to 5 kilotons of TNT going off. And that clearly doesn't happen around us in the universe. We would have noticed it by now if it did. But it's exactly the sort of process that did go on in the very early universe. Matter and antimatter met, annihilated with such energy that this energy was carried off by very energetic photons that then split to new matter-antimatter particle pairs that then went off, annihilated again, and so on. And this process continued as the universe expanded. And as the universe expanded, of course, so it also cooled. And when the universe cools, all the particles in it lose energy. And so eventually, after about a minute or so, after the Big Bang, what we found was, well, not what we found, but what we understand to have happened is that particles in it no longer had enough energy in their annihilations to make a photon that had enough energy to make a new particle-antiparticle pair. And this whole cosmic battle between matter and antimatter was stopped at that point when the universe was a minute old. And what remains now in the universe is a consequence of an imbalance that must have existed between matter and antimatter at that time. Otherwise, we wouldn't be here. And so something's happened in the first minute of the universe to tip the balance slightly in favor of matter. And we don't know what that is. We don't know whether it's due to some new exotic type of matter that we haven't discovered yet, or whether it's due to the fact that we haven't fully understood the behavior of the matter that we know about. And that's important for us to find out about. Last problem, which is potentially the biggest. I've only told you what we understand about the observable universe And astrophysicists tell us that's only 4% of the whole thing. 23% of the universe consists of something called dark matter, whose presence is inferred from studying the effect of gravitation between galaxies. 73% of the universe consists of something called dark energy, which is thought to be responsible for the acceleration of the universe. Now, in particle physics, we have absolutely no idea what dark energy is. And to be fair, we also have no idea what dark matter is either. But at least we have some theories that attempt to explain what it's made of, what it consists of. And one of our favourite theories at the moment that might explain dark matter is a theory called supersymmetry. Now, the notable thing about supersymmetry, the key to supersymmetry, is that it invokes a new symmetry in nature between our matter particles that I've told you about and the force-carrying particles I've told you about. So in practical terms, what this means is that supersymmetry introduces a new supersymmetric particle partner for each one of these matter and force-carrying particles, but such that supersymmetric particle partners of matter particles behave like force-carrying particles, and supersymmetric particle partners of force-carrying particles behave as matter particles, and this is how the symmetry comes in. So if supersymmetry were correct, our universe would expand dramatically to all these different building blocks, and I've tried to denote all the supersymmetric particles with these little squiggles to stop it being quite so confusing. Now, the key to understanding dark matter, why supersymmetry is such a good candidate for that, comes about because the lightest supersymmetric particle, which, depending on which type of supersymmetry you subscribe to, is either this one in red or this one in red, this is a really good candidate for dark matter. It's a really good candidate because it has mass, so gravity can act on it, and it's also experimentally completely unobservable, just like dark matter. So it fulfills all of our criteria. Now, it might seem a bit daft to have a theory that tries to explain what dark matter is made of by producing a particle that we can never hope to see. But in fact, if supersymmetry were correct, we would hope to see, if we couldn't see these particles, we would hope to see all these other new particles that supersymmetry predicts. So, in other words, if we were to run an experiment, discover a new particle, measure its properties, and find that they were consistent with what we were to expect from this theory, we could be confident that supersymmetry was a better description of the universe. We could infer the existence of this lightest particle that might explain dark matter, and thus we could explain far more of the universe than we can already. However, supersymmetry is only a theory, and it's only a theory because, again, we've never seen experimental evidence for any of these particles that it predicts. So you can see that we have many open questions in our understanding of matter. There's much of the universe that we haven't explained yet, or that we can't explain, or that we don't know how to explain. And it's not just the three questions I've told you about. There are many others that are fundamental as well. So how do we propose to fill in the gaps in our knowledge? Well, remember, we're trying to find out what matter consists of. We're trying to look for new forms of matter. We're trying to study the behavior of that matter. In order to do that, what we need is a huge microscope, in bare terms, to look at matter at this very deep level. In bare terms, we need something like a time machine to emulate the very start of the universe, because these were the very energetic conditions when the particles we want to study were unlocked from other forms of matter and moved around freely so we could observe them. So in other words, to study these particles, we need particle accelerators, because particle accelerators can exhibit some of the properties of both of these. Now, a particle accelerator, in principle, is very, very easy to understand. All we do in a particle accelerator is we take a collection of particles, and these could be fundamental particles like electrons, or they can be other types of particles like protons. We take as many as we can, we accelerate them to as high an energy as we can in two beams, and then we smash these beams together. That's the principle by which a particle accelerator works. Now, a particle accelerator can behave as a microscope because of a property of quantum theory, now, which is really, really neat. So in quantum theory, any object can behave as if it were a particle, so it can have a position, or as a wave, so it can have a wavelength. And it just so happens, if an object is very, very energetic, then its wavelength is very, very small. And if its wavelength is very small, it's sensitive to very small distance scales. It can resolve very small distances. And if you can resolve very small distances, you have a very good microscope. So that's why, in particle accelerators, we try to make our beams as energetic as possible. It's so they're sensitive to as small a distance as possible, which is very important, as you've seen, when you're dealing with our particles, because they're very, very small indeed. So this is just a picture of an example to show you what I mean. If we have a beam of particles, that's what the arrow is here. And we want to look at a proton, which is this blob here. We'd find if we had sort of a medium energy beam of particles, it might well have an associated wavelength like this. That means it's sensitive to a distance scale of about this size. So if we fire it at a proton, we would interact with a proton as a whole. We'd never see anything inside it. We'd never uncover the fact that the proton is not a fundamental particle. To do that, we'd have to have a higher energy beam. A higher energy beam would have a shorter wavelength. It could probe inside the proton and pick out our other fundamental particles. So this is why in a particle accelerator, we always try to get the largest energy that we can. It's to resolve as far inside matter as is possible. Now, I also mentioned that a particle accelerator can behave like a time machine. I don't literally mean it is a time machine, of course. That's a bit sensationalist. But what I mean by this is that it's capable of recreating conditions that last existed billions of years ago. In this sense, it's like a time machine. And we can do this if we take our beams of particles and we collide them together. Because in that collision, in that very small space, for that instant of time, we have recreated energies that last existed in the universe soon after the Big Bang. And that's important from our point of view, because if we can recreate those very energetic conditions, then we can also recreate the fundamental particles that moved around freely then. And if we can build an experiment around this collision point, we can detect them, we can study them, we can learn about them. And that's the principle we use in particle physics to learn about what matter is made of and what the universe is made of. So let me give you a real-life example of a particle accelerator. This brings us now to the LHC, and I can start telling you about that. The LHC is a particle accelerator. It's situated at a place called CERN, which is the European Centre for Particle Physics, which is near Geneva in Switzerland. And on the left-hand side here, you can see an aerial photograph of the LHC. So let me put this in context. At the back here, I'm afraid it's a bit blurry, at the back we can see the Alps. This blue region is Lake Geneva. Geneva Airport is this strip here. And in red, this circle is the 27-kilometre-long line that is the LHC accelerator. Now, if you were to fly over the Geneva countryside, of course, you wouldn't see a red line on the ground. That's because the LHC is 100 metres under the ground. If you flew over the Geneva countryside, you wouldn't notice anything amiss at all. But if you could go 100 metres underground, you would see a tunnel. And through the tunnel is a continuous chain of magnets linked around that guide particle beams around in a circle. So when the LHC starts up, which will be soon, what will happen is that we'll have two beams of protons in our accelerator, and they'll circulate in opposite directions to each other. And they'll be accelerated to such high energies that they'll be travelling at almost the speed of light. And then they'll be brought into collision at 4 points around the ring where we'll build our experiments. And this will happen, these collisions will happen not just once, but 40 million times a second. That's 40 million possible snapshots of the early universe every second for us to study. Now, some of you might already have heard of CERN and the LHC, not least if you've read this book by Dan Brown, where CERN and the LHC make a sort of guest appearance near the start. In this book, the LHC is actually called the Large Machine, and it's a technological marvel of matte black and stainless steel. Well, I'm afraid in real life, if you were to go down to the LHC, you'd see it's a rather dusty tunnel. It doesn't look very impressive at all. But in terms of what it can achieve, it's far more fantastic than any fiction. Let me show you what I mean. This is an animation that shows you what goes on inside the LHC. Protons come in from one side, they meet protons coming from the other side. They collide together, they create new particles that fly out and are detected in our experiments. That's the process that's going to go on 40 million times a second when the LHC starts. Now, if we want to understand what's going on here, we have to make recourse to two of the most complicated theories of 20th century physics. To start with, because our protons are moving so fast, they're traveling at almost the speed of light. If we want to understand where those protons are, we have to use Einstein's theory of special relativity to do it. Otherwise, we just have no idea where to find them. And if we want to work out what happens when the protons collide together, we have to use quantum theory. And quantum theory is a really, really strange theory because here it's impossible to know anything absolutely. That's forbidden. All we can do, the best we can do, is to work out the relative probabilities for different things happening. We have to cope with things like particle and antiparticle pairs popping in and out of existence at whim. It's a very strange universe, and it's completely at odds with our normal conception of it and our normal experience. But it's the theory that we have to use if we're going to understand and make sense of what goes on inside the LHC. And it's not just, if you like, the theory, the language of the LHC that's complicated and almost at our limits. Let's not lose sight of what it is that the LHC is going to be doing. The LHC is so powerful that when these beams collide, it will be recreating conditions last seen in the universe a billionth of a second after the Big Bang. That's when the universe only had time to expand to be the size of a full stop on a page of text. And that is just amazing to me. But it's not just the physics that's not amazing. It's not just what LHC can do inside when it operates that amazes me. The whole construction of the LHC was a civil engineering triumph. The LHC is actually the largest piece of scientific apparatus in the world. When it was built, it was the second largest, well, when it was built, it was actually the first largest European engineering project, I think. It's now the second largest, second only to the Channel Tunnel. And when this tunnel was constructed 100 meters underground, it was constructed with such accuracy that when the tunnel boring machines that dug out the hole started off going around in different directions around the ring, when they met up 13.5 kilometers later, they were accurate to within a centimeter of each other. And that is remarkable precision. This tunnel, now it's been made, is now filled with a whole series of superconducting magnets which keep our beams moving around in a circle. These magnets are really powerful. They're superconducting. They operate at a temperature even colder than the outer space around the Earth. And these magnets need to be so powerful because our beams are so immensely energetic. The beams at the LHC have the energy of an aircraft carrier about to take off. It's not something that you'd really want to stand in the way of. Now, I'd just like to really set the scale of the LHC in your mind, having told you how big the fundamental particles that we want to study are, because there's quite a difference, as you'll appreciate, in scale. And the best way to appreciate the scale of the LHC is to compare it in size to the Circle Line on the London Underground. And this isn't as daft as you might think, because they're actually quite similar. The Circle Line is not quite as long as the LHC. It's only 22.5 kilometers, and it's not quite as deep underground either, only about 15 meters as opposed to 100 meters. But the bore of the tunnel of the LHC and the Circle Line is very, very similar. So the next time you're sat on a tube going around the London Underground, just think you're in a very similar environment to a proton going around the LHC, except unfortunately there's no way you're traveling at almost the speed of light. You're probably traveling at a speed equivalent to a technician as they go around the LHC trying to mend magnets, where I'm afraid our favoured mode of transport is just a bicycle. So the LHC then is the equipment that recreates particles for us. It's the equipment we use to create the fundamental particles that we want to study that hold the secret to understanding the structure of matter in the universe. Now, we detect those particles with our experiments. Now, I told you that we have 4 experiments at the LHC. 2 of these experiments, which are called ATLAS and CMS, are large and general purpose in nature. And what I mean by this is that they cover as much of the area around the beam collision point as possible. They're designed to be sensitive to as many different types of particles as possible and to collect as many particles as possible so that they can make measurements of as many fundamental particle species as there are, ones that we know about, ones that we don't know about. And the two other experiments were designed with a specific aim in mind. The LHCb experiment was designed to look into this question of why there's so little antimatter in the universe, and the ALICE experiment was designed to look into quark-gluon plasma. Now, having set the scale of the LHC for you, I also want to set the scale of the experiments because they're also large. So I do that by showing you how big the ATLAS experiment is. Now, this is a picture of ATLAS on the left-hand side, and you might already have seen it before because it's appeared in a number of magazines and newspapers. This was actually taken about, well, just over a year ago when ATLAS was in full swing of construction. In fact, ATLAS is still being constructed, but it's almost finished now. So what we see in this picture are 8 rings, which are the magnetic skeleton, if you like, of the experiment, and lots of support structures holding it together. If you can make it out, there's a little circle in the center here. That's where one of the proton beams of the LHC comes into the experiment, and you're looking in the direction of the other proton beam coming in. So when the LHC runs, these beams will meet each other somewhere in the center of this enormous volume. They'll crunch together, they'll make new particles. These particles will fly out in all directions, and this entire volume of ATLAS will be instrumented with particle detectors that will detect these particles and identify them. Now, ATLAS is really, really huge. This person who stood in the front of it is actually a normal-sized person and not especially small. ATLAS is the size of a 5-story building. That's the size of a cathedral 100 meters underground. It's absolutely enormous. It's the largest particle physics experiment that we've ever built. And it's not just large in size. There are some 2,000 particle physicists from all over the world that collaborate together on the ATLAS experiment, because the LHC is really a global enterprise. And you need this many particle physicists to design and build an experiment like ATLAS because it's very large, it's very complicated, and it's also very, very expensive. So that's what an experiment looks like from the outside. But I'd like to also show you what it looks like from the inside as well, show you what it consists of when everything's made. And every experiment at the LHC is constructed along similar principles. And we design experiments to consist of a series of layers of detectors of particles. And every layer, every particle detector layer, has a different job to do. So immediately around the beam collision point, we have a layer of detectors which are designed to measure the position of any particles that are produced as they fly through. This is a picture of a typical particle detector. This was actually made for the LHCb experiment. It's a silicon detector, and it was made by the University of Liverpool. And the sensitive part is this silver half circle here. This detector is so precise that it can detect the position of anything charged going through it to the precision of 1/10 of the thickness of your hair. It's remarkably precise. And every experiment at the LHC has detectors like this, either arranged in a line or arranged in a circle, such that particles will pass through many of them, and we'll be able to trace out their path, to reconstruct how they've flown through our experiment. So this, for example, is a picture of the silicon detectors in the ATLAS experiment. These are arranged in concentric circles, and what we see here is a silicon detector being inserted inside another layer of the tracking detectors. And if we were to look at the tracking detector system as a whole, which I've shown here for the ALICE experiment, we'd see it's actually quite big. A particle produced here has to go through 1.5 or 2 meters of measurements. So if we can read out information from this detector when there's been a collision, we'd have a series of hits. And then we can do a join the dots exercise to work out where particles have gone in our interaction. Well, that's the first layer of detectors. Then we have another layer of detectors after this that we call calorimeters. And calorimeters measure something different. They measure energy. And they also have the nice effect that different types of particles will stop. They'll be absorbed in different layers of the calorimetry. So besides measuring energy, they also help us identify what sort of particles we have. So this is just one picture of a calorimeter. This is the first layer of calorimetry for the ALICE experiment. It lies outside that tracking chamber you've just seen, and it's actually built of an array of lead glass crystals. And there's one final layer of particle detector that stays on the outside of the calorimeter, and this is called a muon detector, because a muon is the only fundamental particle that survives its passage through the rest of the detector. And that means that muon detectors are really, really large. They're the largest type of particle detector. Here's a picture of a man working on one of the muon detectors of the ATLAS experiment. And this is something of a hallmark. If you work on any aspect of the ATLAS detector, it's so huge that you need a crane to reach it. And perhaps the scale is maybe even more apparent on this picture, where you can see there are two physicists here in the upper right-hand corner, busy connecting together muon detectors. But to get there, they're suspended on a crane which is some 20 meters above the ground of the experimental cavern. That shows you the size of these experiments. So that's what they look like inside. But the principle is very, very simple. We have a fundamental particle being produced in a beam collision in the LHC. These particles and the other particles they produce fly out in our detectors, and depending to where they get to, that enables us to identify them. So if we read out all the information from our detectors, we analyze it with computers, we can reconstruct where our particles are gone, what type of particles we have, and if we compare that to our theoretical predictions, then we can work out, we can infer what sort of fundamental process we had in the beginning, and if this fundamental process and particle is behaving as we expected. And if it's not, perhaps we've made a discovery. And if we do this again and again and again, from this series of snapshots, we build up a much bigger picture of what matter's made of at its deepest level. So that's the idea. That's how we perform our experiments. So in the final part of my talk, having shown you how we build our equipment, how we make our particles, how we detect them, now I want to give you an example of how we make sense of this data and turn it back into knowledge. And I'm going to give you an example of how we might try at the LHC to look for the Higgs particle that I've told you about before, because it's so important to us that particle physicists have already invested lots and lots of time in trying to find strategies for finding it. Now, we do have a theory that tells us about the Higgs, and because we have a theory, we can simulate what we expect the Higgs to look like in our experiments. And the Higgs will look something like this. This is a snapshot of a Higgs particle taken in the CMS detector. Now, it looks confusing, but our problem isn't trying to understand what's in this snapshot. Our problem is something a little more fundamental than that when we come to trying to discover something like this. Our problem is obtaining that snapshot in the first place, because remember what goes on inside the LHC. Two beams of protons, and they collide together 40 million times a second inside 4 experiments. Now, our theories tell us that the Higgs can be produced anywhere, inside any one of our experiments, inside any one of these collisions. So if we want to discover where the Higgs is, if we want to make a discovery of a Higgs, we have to reconstruct very, very quickly what's happened in as many of these collisions as possible. Otherwise, we might not find the Higgs at all. And that really is where our problem lies. It's quite a challenge. So again, here's another picture of a Higgs that's been produced. What's happened here is that buried in this mass of other particles, a Higgs has appeared and decayed instantaneously into 4 other particles, muons. They're shown here on the bottom. It's a bit simpler to see them. They're the green lines. Now, our theory tells us that we might expect to see a Higgs like this in one of our experiments once every hour or two, which is quite a lot, really. So you might think it's actually very quick to discover a Higgs. So once the LHC switches on, we might be able to make a discovery perhaps in the first day. Well, the problem is not that we get a Higgs produced once every hour or two. The problem is finding that Higgs amongst the 40 million things going on every second. It's a huge combinatoric problem. And if we suspect that any of those 40 million things per second might contain a Higgs, we want to read out and store all the information from the detector, and that's at least 100 million channels of electronic information. So finding something like the Higgs, or supersymmetry, or anything else is rather difficult. And the selectivity problem is quite immense. Looking for the Higgs is like looking for one person in 1,000 world populations. It's like looking for a needle in 20 million haystacks, if you like. You know, it's quite a challenge, in other words. So at this point, you might think that despite having overcome our engineering challenges in building the LHC, our design challenges in making the experiment, we might fall at this final hurdle of actually making sense of what they're all doing. But it's not as bad as that. It's simply a question of analysing a huge amount of data. Now, it's been estimated that every year the LHC is going to produce enough data, if you were to consider writing it out, to fill 14 million CDs a year. If you were to pile up these CDs, you'd make a column 20 kilometres high. That's 1 million times more information than the world annual book production. And yet, that's the sort of size data set we need to analyse if we're going to unambiguously discover the Higgs and make a statistically significant discovery. So we can do this. It's not insuperable. It simply demands that we have lots and lots of computing power to do it. And it's been estimated that if you want to analyse this much data, you're going to need something of the order of 100,000 computers to do it. And you can see immediately there's another problem here, because no one particle physicist has 100,000 computers at their disposal. No one country's worth of particle physicists has 100,000 computers at their disposal. So if we're going to meet this final hurdle in our challenge of understanding matter, we have to arrive at a new way of fulfilling our computing needs. And that's what we've done in particle physics. We've developed something which is called the grid. Now, the grid is like the World Wide Web, but the next step up. And the World Wide Web, by the way, if you didn't know, was invented at CERN in the 1990s for particle physicists to share information with each other. So, in the way that anyone can use the web, if they sit at a computer that's networked and it has a piece of software installed on it called a browser that enables you to access information, the grid operates in a similar way, except here, if you have a grid user sitting at a computer that's networked now with grid software installed instead of a browser, then that grid user can access not just information and data, but they can also access all the computing power of all the other computers connected to the grid. So in this way, if you connect enough computers together all over the world, you can make a distributed computer that to the user just looks like one big supercomputer, and one big supercomputer, hopefully, that can fulfill their processing needs. And that's not so daft, because remember that particle physics is a really global operation now. Atlas, I gave you the example, has 2,000 particle physicists from 150 institutions all over the world. If all of those institutions connect computers to the grid and data storage facilities and connect them up with high-speed interconnects, then you can make a facility which is large enough to process this much data and hopefully end up with a discovery of the Higgs. So the grid does exist. There's a prototype which works already. And this is a map of grid world. So what you can see here, wherever there's a green splodge, that's an institution which has put computers onto the grid and connected them up together. And everywhere you can see a line, that's where a particle physicist has written a computer program, sent it off to the grid, and this program is travelling the world, collecting its data and sending back its results. And the UK actually is quite a major player in the grid. As of last year, it had put over 5,000 computers onto the grid, and many more are being added all the time. Last year, over 1 million computing jobs ran on the grid. And it's not just particle physics that can make use of a resource like this, of course. It's any computationally intensive problem. So, as well as particle physics last year, other jobs that ran on the grid to design drugs to combat avian flu and malaria. So, the grid is the last missing link in the journey the LHC is starting us on into discovering more about matter. The grid will allow us to analyse all the data that we take at the LHC, make sense of it, and hopefully discover new forms of matter or make discoveries about particle behaviour. And the grid, besides being the last link in this chain, is also the last item in my talk. It brings my talk to a finish. So I hope in this talk, which was a very, very brief whistle-stop tour of all of particle physics, everything we don't understand, and the LHC, I hope I've managed to give you a picture for what particle physics is, for what we're concerned with, for what we study in the universe, and what we don't understand about the universe yet. And I also hope I've conveyed something of what the LHC is to you too, what it looks like, how big it is, how we're going to use it to tackle our problems. And I'll just finish by asking one question, which is, what do we think we're going to find when the LHC starts up and reaches its highest energies next year? Well, we have some ideas about what we're going to see because we've already looked in previous experiments, so we're not starting from scratch. But to be honest, we don't really know what we're going to see because the LHC is so powerful, it probes matter so deeply, it accesses a region that we've never been able to look into before. And because we've never looked there before, we just don't know what we're going to see. And that's what makes this whole venture and enterprise so incredibly interesting and exciting. So in answer to this question, what will we find? We don't know. And we have to wait, like you have to wait until next year to find out more and find out what secrets the LHC is going to reveal to us about the universe. Thank you.
Thank you, Tara, for a very inspiring lecture. Tara is very happy to answer questions, so I hope there are going to be a lot of questions. Has anybody got a question? There's a question there. Could you stand up, please, and wait for the microphone?
I'm losing my voice. Philip Coghlan, if I understood you, I think you said the Higgs particle was responsible for imparting mass to the other particles. Is that right? So if you find the Higgs particle, does this help you in any way confirm the idea that it does impart mass to the other particles? And if so, how does it help you do that? Hope that makes sense.
It does make sense because you've raised an issue that haunts us in particle physics, which is if we discover a new particle, how on earth do we work out what on earth it is? So if we find a new particle, our first reaction is to compare it against all of our theories that might predict something like that. And because we have a theory that predicts what the Higgs looks like, also to some extent what mass it might have and how it behaves and what other particles it might decay to in our experiments, what signatures it will give us, we can compare anything we've seen against our theoretical predictions to see if it's consistent. And if what we see in our experiments is consistent with our theoretical expectations, then at a certain level, we're confident to believe that it is a Higgs. So that's how we discover it. Now, if we were to discover a Higgs and it were to display the properties that our theory predicts, then for us, this would answer our question about mass because our theory represents our explanation of mass. So if we find an experimental verification of that theory, then that tells us that we were on the right track. It's confirmed that our argument was correct. Does that answer your question? Have I missed something?
I've still got an element of doubt about it, but I see what you mean.
It's fair to say there's always an element of doubt because there could always be another type of process that could fulfill the role of the Higgs. That theory may not be correct. We might discover a new particle which isn't actually the type of Higgs that we think it is. And there are other theories, competitive theories to the Higgs theory that I told you about that predict a type of Higgs particle but which has different properties. So I've given you a very general answer. In reality, it's much more complicated than that. There's an awful lot of work to do before we can claim to have discovered anything with confidence. So rest assured, we do work hard at trying to understand what we find.
Yes, there's a question here, and then over there.
The universe...
Sorry, could you wait for the microphone?
The universe as we see it today is made up of up-down quarks and electrons and photons and gluons and so on. I presume that the Higgs would have only existed, and the top quarks and those things would only have existed just after the Big Bang. They don't exist anymore, do they? They've passed on their energies down the line to the proton and the electron, or have I got it wrong?
No, it's actually an area I find quite complicated, which is why I'm being hesitant now. It's true that if we look around us at the moment, just where we are on the Earth, energies are so low that a real Higgs particle doesn't exist. It decays instantaneously. That's why in our experiments, when we recreate a Higgs for an instance of time, that very energetic environment doesn't last in our beam collisions. It dissipates rapidly, and that's why our Higgs decays. It doesn't last any longer. But we have, because of quantum theory, well, no, I'll leave it there. We have real Higgses at the start of the universe, and they carried out their job of giving mass to particles and made everything look the way it does to us today. That's true.
Thank you.
There's a question on the front row, another one here.
Is there enough computing power, and is the collider powerful enough such that if the Higgs does exist, we'll find it? Or put another way, if we can't find it, if the answer to both those questions is yes, and we can't find the Higgs, does that mean we're going to have to rewrite everything?
It's a really good question. Two really good questions. So I mentioned that our theory of the Higgs is already embedded in our standard model of particle physics that we use to understand everything. And that means that we can constrain the properties that this Higgs has from our experimental measurements, because this theory plays a part in every single one of them. It's a free parameter, if you like, which is constrained by our experimental results. So in fact, we know already that if that Higgs exists, if it really is a proper particle, that its allowed mass, for example, can't be just anything. We know it has to lie in a certain quite narrow region, which is where we'd expect to find it. We also know the sorts of particles it will decay to, the sorts of signatures that it will leave in our experiment now quite well. If it exists, we've pinned down its properties to quite a good degree, and that allows us to devise our strategies for looking for it. Now, of course, that only works if there is, well, it only works if there is a Higgs, but it also only works if there is a Higgs that theory describes. As I alluded to before, it is also possible for there to be other particles to fulfill the role of the Higgs. There are other theories that can explain it. I've just told you about the most generally accepted one. And in that case, any constraints that we have inferred from our experimental measurements no longer apply. And in that case, what we might find when we start the LHC is that we might find a particle, but in a completely different place with completely different properties to those that we think a Higgs should exhibit, and that would give us pause to think. But we do believe we should find something. And we believe that we should find something simply because our theoretical predictions break down if there's not a particle to fulfill the role of the Higgs that has a mass below a certain value. And that mass is accessible at the LHC. We should see a particle with that value. And if we don't see a particle with a mass of that value, then that does imply that our understanding of particle physics isn't correct, and we would have to think again at that point.
There is a question here, but maybe I can insert a question here, because the first time we've broadcast this on the web, and we've got a question back from the web, so it's quite exciting, this. It says, loads of data will be generated by experiments. How long will it take to analyze it all? And will we be able to spot everything of use, or is there any danger that we'll miss something unexpected? Sounds like a question from quite high up. Shall I read it again? The first one. Loads of data will be generated by the experiments. How long will it take to analyze it all?
Shall I start with that one?
Yes.
Okay. So, in fact, it will take us quite a long time to analyse the first data that comes out of the LHC. And that's not just because of the amount of data that we have. It's because we also have to understand the response of our experiments, and we have to understand the way that they operate in order to be able to interpret their data correctly. And this is something we're not going to be able to do straight off. We're going to have to understand the data, calibrate it, and reprocess it, and examine it, I would have thought, maybe 2 or 3 times before it's in a condition that we can really start making inferences about what's in it. So in terms of timescale, that's difficult. But what normally happens in a particle physics experiment that starts off is that it takes about 6 months or so at least to understand what the detector's doing in the first amount of data and to make sure every part of it is responding in the way that you expect. And then after that, you can build on your understanding and then start to hopefully make discoveries. So in that sense, the first part of the question means it would take at least, I would have thought, 6 months, unless there's something that's so extreme in the data that we haven't even thought about, sticking out like a sore thumb, in which case we can probably see that sooner.
And will we be able to spot everything of use, or is there a danger that we'll miss something unexpected?
Yes, that there's always a danger. At the LHC, remember, we have 40 million collisions happening per second inside every experiment. And it's impossible for us to record all of these. Physically impossible. There's just too much data. So what we have to do is to only record a subset of this data. It's all we can manage. Maybe something like between 200 and 1,000 of these collisions is all we can manage. So in order to sift through all those collisions to decide what holds interest for us, what might help us understand matter more, we have to apply a very, very fast decision-making process that works in a microsecond or less. And there's always the danger there that we might inadvertently miss something. So, of course, we try not to do that. We try to think of strategies that cover us against this eventuality, because if you haven't recorded a collision, there's no way you can analyze it later. If you can't analyze it later, you can't discover anything with it. So we try to make sure when we collect these events that we also collect them, some of them at least, in an unbiased way. So we also take events that we don't know offhand will be interesting or not, just in case there's something unusual in the data that we haven't thought of, that we can then use those events to try and understand. And if that's the case, then of course we can reevaluate the way we choose our events to write out and record, and then hopefully understand this a bit better. But yes, this is rather a lot of work. It's at least half of an analysis in physics to devise the method by which we sift this data.
There's a question just in the third row here. Oh, just there. Oh, yours been answered. Somebody behind.
Referring to these 40 million collisions a second, these colliding protons, are they all going the same speed, or do they have a Maxwell-Boltzmann distribution?
Oh. Well, their energies are pretty close because of the way that the accelerator operates. So the way particles are accelerated inside an accelerator is that, well, what's an easy way of describing it? Basically, the accelerator is operated in a mode whereby particles of the energy you want just zip through. Particles with a little less energy feel a stronger accelerating force to let them catch up. And particles that are going a bit faster slow down because they don't experience as much acceleration. And that happens all the way around the ring. And this has the effect of making sure that we don't have a big spread of energies. If we have particles that had a lot less energy, they would just be lost from the accelerator. They wouldn't continue to go round. So that's how we ensure that on average we have that particular energy of our beam. Now, there may well be a small distribution in this. It may not just be one value, but we don't really care about that, because what we find where inside the LHC, when we collide protons on protons, because of the energy, we're not actually colliding all of the proton with all of the other proton. Because remember, a proton isn't fundamental. I told you it's made of 3 particles called quarks, and these all carry a certain fraction of the energy. And what we find is that some part of this proton will collide with some part of this proton, so we never actually get the full benefit of the proton energy anyway because of this. So yes, the protons have more or less the same energy as they go round, pretty nearly so, but we don't tend to see that in our collisions. So the fact that they're not exactly the same energy doesn't really matter to us.
There's a question just here.
Hi. I've got 2 questions, actually. First one is, I remember reading a while ago that Fermilab had actually searched a good proportion of the energies for the Higgs boson and hadn't found it. And I was wondering if you thought that might be a problem. And the second question, unrelated, is about the supersymmetry aspects of the experiments. And And two parts to that. One is, I was wondering, in a purely supersymmetric universe, would the increased number of charge-carrying particles imply that there would be more forces in that universe, more than just the four forces? And given that it's being used as a model for dark matter, weakly interacting dark matter, how do you know you're going to detect supersymmetric particles at all?
All right, that's three questions. So I'll start off with the first one, and then just remind me if I miss out some of them. So your first question was about Fermilab looking for the Higgs, and the fact that it's covered the energy range where we might expect to have found the Higgs. Well, you're quite right. The Fermilab accelerator is maybe a factor of 10 less powerful than the LHC. So in principle, it's able to have enough energy to create a Higgs of the masses we expect a Higgs to have. But I told you that searching for the Higgs is a challenge. And you saw what a challenge it was at the LHC. So although we found a Higgs being produced once every hour or two, it is in fact very, very difficult to disentangle those Higgses from the many other things that are going on every second, particularly so because many of those collisions that are happening per second look pretty much identical to the Higgs. And this is what has stopped the tevatron discovering the Higgs, we think. We think that's the reason why the tevatron isn't as sensitive. It doesn't have as much data as the LHC will produce. So although in principle the tevatron has enough energy to create a Higgs, and indeed it does so, I forget how often, however many days it should create a Higgs if it exists, it simply doesn't have enough data for us to unambiguously disentangle that signal out from it. So they would feel really sick if they had the Higgs in their data, yet didn't have the statistical precision to bring it out, but that's the case. So, and your second question was about supersymmetry, and correct me if I'm wrong, I might have not remembered, but whether this huge multiplicity of particles has...
Well, the fact that there's more in the supersymmetric universe, it reverses, so there's more charge-mediating particles in supersymmetry than there is in normal matter. So there's 12, I think, instead of 4. Does that imply a larger number of fundamental forces in a purely supersymmetric universe, or doesn't it imply anything?
No. We think the same number of fundamental forces applies. There's not a new supersymmetric force, for example, that holds supersymmetric particles sort of together in addition. Supersymmetry just invokes a symmetry between matter and force-carrying particles, but it doesn't invoke any new forces in that sense. It just ends up by introducing new particles into the universe. And your final question?
Given that its supersymmetry is being used as a potential model for dark matter, which is weakly interacting or thought to be weakly interacting, how do you know the real matter apparatus will detect these supersymmetric particles at all?
Right, I remember now. So we don't expect that they will detect the dark matter candidates, because that's the whole point about them being a dark matter candidate. They have to hide somehow, they have to be invisible. But the other supersymmetric particles aren't. And we should expect to see those. We should expect to see them in the same way that we see our other matter particles. They should appear in our data. The fact that we haven't seen them implies that if supersymmetry is isn't a theory, if it's a description of the universe, that implies that these supersymmetric particles must be much more massive than we've been able to access so far, which is a little bit strange, but it's not impossible. It can happen in the theory. So we should be able to see them. There's no reason why not.
Well, we've run out of time. There's one very quick question at the end. Very quick, because we actually run out of time.
Thanks.
Stand up, please.
Yeah. We've been hearing a lot about the theory of strings. So is that in perfect agreement with the Higgs boson if it does exist?
Ooh, that's an awful question. I'm not very up on string theory. To be honest, I'm not actually sure what string theory says about the Higgs. All I know about string theory is that it's a way of it could be a way of incorporating gravity into our description of the universe. And I'm not sure how our Higgs theory fits into that. So I can't really give you an answer on that, I'm afraid. I don't really know the answer to that. I don't offhand know, sorry. That's a question above my level of knowledge. So sorry, what depressing way to finish the questions.
sad that we have run out of time. I'm very much looking forward to Tara coming back and telling us what she has actually found. So thank you very much, Tara. On behalf of us all, it has been a very illuminating and entertaining session. Thank you.
And that will bring us on neatly to the LHC itself. So I'll describe what the LHC is. I'll tell you about the particle accelerator and how we use it to generate the fundamental particles that we want to study and understand. I'll tell you about the experiments that we build there to detect these particles. And then I'll finish my talk by telling you how we make sense of the data that we collect in our experiments, what we might see in our data, and how we might go about making the sorts of discoveries that will allow us to learn more about matter and the universe. So let me start off with the particle physics. And before I tell you what we understand about the universe at the moment, first of all, I want to set the scale of the smallness of the fundamental objects that we're talking about. And I find it most helpful to do this by means of a sort of reference scale. So this is my reference scale. It's a person, and it's a sort of physicist person. They're only about 1 meter tall. This is my scale of reference. So if we were to look at this person, the smallest thing that we could see with our naked eye would be the size, the thickness of the hairs on their head. A human hair is about 100,000 times smaller than a person. And if we could get powerful microscopes so that we could zoom into a hair by the same amount again, look 100,000 times into a hair, we would see that a hair consists of atoms. You could fit about 100,000 atoms across a human hair. And that we're trying to understand in particle physics. And that's the sort of thing whose behavior we're trying to understand. So that's set the scale for you. Now I'd like to tell you about what we know already about matter and the universe. And in particle physics terms, you can express the universe very, very neatly. So we think that all matter in the universe is formed out of 12 fundamental types of building blocks, 12 different types of fundamental particle. Now, this might not look like much to show for 40-odd years of research, but then we're great reductionists in particle physics. We really can get down to this level. So of these 12 fundamental particles, 6 are of a type that we call quarks, and 6 are of a type we call leptons. And the sorts of fundamental particles that are most common around us here on Earth are up and down type quarks, because combinations of these form protons and neutrons that we find in atomic nuclei, which are then orbited by electrons to make atoms. And we know that everything we see around us on Earth is made of atoms of one sort or another. And these other fundamental particles are more common in higher energy environments than we typically have around us here on Earth. So this is what particle physics says about the universe, but it's no good just unraveling matter to its constituents. In particle physics, we also want to know how to put these things back together again to make the universe look the way it does. And we think that there are 4 fundamental forces. And if we could get an even more powerful microscope, we would see that an atom isn't fundamental. It's not a fundamental particle. And by that, I mean it has structure. It consists of other things. If we could look deeply into an atom, we would see at its core it has a nucleus, which consists of particles we call protons and neutrons, and these are orbited by electrons. So picking a more powerful microscope and zooming into here, we'd see a proton, for example. A proton, a constituent of an atom, is about 100,000 times smaller again than an atom. And if we could pick an even more powerful microscope, and this is where particle accelerators come in handy for reasons I'll tell you later, then we would see that a proton's not fundamental either, because that's got things in it. It consists actually of 3 fundamental particles that we call quarks, and quarks are at least 10,000 times smaller than a proton. Now, quarks are an example of something we believe to be fundamental in particle physics, and that's because we've never been able to look inside them and find something else. They're point-like to us. And when I say they're at least 10,000 times smaller than a proton, we haven't actually been able to measure them. They're so small that the 10,000 times just comes from the limit of our experimental resolution. So to set the scale of these fundamental particles, to fix it in your mind, a fundamental particle, like a quark, is almost as small compared to an atom as an atom is compared to you. That's the size of particle that we're dealing with.
The microphones. Dr. Tara Shears is a Royal Society Research Fellow at the University of Liverpool. She gained her PhD at the University of Cambridge in 1995. Since then, she's played a key role in large experiments, OPAL at CERN, and also at CDF at the Tevatron Collider at Fermilab near Chicago, and she's still working on that experiment, which is the biggest accelerator at present working. In 2005, Dr. Tara Shears received the Cavendish Medal for the Outstanding Young Research Fellow, and since then, she has been working at the LHC. This is a very exciting time for particle physics because the LHC, this huge collider, is about to be commissioned at CERN after many years of preparation, at least 20 years. So it's, without further ado, it's a pleasure to introduce Dr. Tara Shears, who will talk on the LHC.
Thank you. So hi, everybody. This talk is about the building blocks of the universe. It's about the fundamental particles that we think are matter's smallest constituents. Because in particle physics, we try and understand the universe from the microscopic level. We think in particle physics that everything in the universe, everything, all matter, is made of the same fundamental constituents. And it's our aim to identify what these are and how they behave. Now, we already know quite a lot about matter and the universe, but we also know that there's much more to understand. And it's for that reason that this talk is also about the LHC. So as Alan has just told you, the LHC is our new particle accelerator. It's the most powerful particle accelerator we've ever built. And the LHC is the facility we're going to use to strengthen and deepen our understanding of matter and the universe. So in other words, this talk is going to be as much about what we don't know as what we do know, and how the LHC is going to help us find out more about everything. So I'll start off this talk by talking about the particle physics, because that underlies everything. I'll tell you what we understand about the universe so far, and then, perhaps more importantly, I'll tell you what we don't understand. And I'll tell you about 3 of the most pressing questions that face us in particle physics nowadays. And then, having told you about all our problems, I'll then show you experimentally how we try to address them, how we try and find answers and solutions to them.